Okay, welcome to part 3 of chapter 16, the chapter on nonspecific or innate defenses of the host. This is part 3 in a 3-part series, so I guess we'd call this the final part, I suppose. I'll finish out the chapter and then be looking for future chapters. We're going to be moving on to the next chapter, which will be mechanisms of pathogenicity. So how do microbes, how are they able to evade our immune system defenses? So that'll be the next chapter. Anyway, so we'll start here with fever. Fever, of course, is an abnormally high body temperature. You can call it hyperthermia, whatever. But fever is a specific type of hyperthermia. It's caused for a reason. There's a causative agent that will bring about a fever and leading to this higher than normal body temperature. So the hypothalamus in the brain is our body's temperature regulation system. The thermostat is what it's often nicknamed, and it's normally set at 37 Celsius, 98.6 Fahrenheit for most of us. And so it keeps this temperature and maintains this body temperature so that becomes the optimal temperature for enzymatic performance and the ability of enzymes to do their thing in our biochemical processes. So how does fever come about? Well, the most frequent cause is infection from bacteria and their toxins, and that's important, and that'll be in our next chapter on the toxins and their ability to cause disease. And viruses as well. So viruses will cause infection or will cause fever as well due to a viral infection. So what happens? This is a very generalized step-by-step process that you can see. I tried to break it down into 4 basic steps. So this would be if you have gram-negative, okay, because endotoxins do cause fever generally, and exotoxins generally do not. And so there are different categories of toxins, and this is something that I will elaborate on in the next chapter on toxins and toxicity and the different classes of toxins and what they do. But generally speaking, gram-negative bacteria release endotoxins, which is actually part of their outer membrane. Those endotoxins, whenever they become ingested by phagocytes, they induce the phagocyte to release a protein that's called interleukin 1. And interleukins are a group of immunomodulatory proteins that help to modulate and regulate immune responses within the body. And there's a number of interleukins, but in this particular case, we're going to look at interleukin 1. Next, then, the hypothalamus responds by releasing prostaglandins that reset it at a high temperature. And again, another group of proteins called prostaglandins. Now, you ask, well, how did we go from the gram-negative endotoxin to the hypothalamus? The gram-negative endotoxin, like I said, induces the phagocytes to release interleukin 1. The interleukin 1 then gets put into the circulation, and eventually this interleukin 1, as it's circulating through the bloodstream, makes its way to the hypothalamus in the brain. When the hypothalamus receives this chemical signal, it then responds to it. So remember, this is how this system of the body is working. A signal has to be put out, and then something has to receive it. And this is how the immune system works, so that we don't have just immune system responses just acting willy-nilly throughout the body whenever it's not necessary. So anyway, these prostaglandins reset the hypothalamus at a high temperature. The body increases its rate of metabolism and initiates vasoconstriction to conserve heat and shivering to raise the temperature through the breakdown of glucose and ATP. So that then will lead to a slight rise in temperature, and due to the hypothalamus promoting all of these and initiating these different bodily responses. When IL-1 is eliminated, meaning therefore there's no more endotoxin being released, vasodilation and sweating occur and the body temperature falls. So rather than having vasoconstriction and heat conservation, we have vasodilation and releasing of heat. And we call this the crisis, whenever the fever then is dissipating. So, fever, are there benefits? Of course there are. Having a fever is a natural bodily process. And so, I don't want you to see fever as being something that's negative, that it's something that is hurting us or detrimental to us. A fever is there in order to tell us that we're sick, basically. Just like we have pain receptors in our skin to tell us that, this is painful, you probably should stop doing whatever it is you're doing. So with a fever, we do derive benefits from it. And what are they? So increased temperature can prevent some pathogens from reproducing. Some bacteria, once you get above about 100.4, 100.5 Fahrenheit, their rate of reproduction slows. Um, Not severely, but enough that it would reduce their numbers. Interleukin 1 helps increase production of T cells. So more T cells means more cytokines being released, which are immune system proteins that we'll talk about with specific immunity. But interleukin 1 serves as a signal in that respect as well, the increased production of T cells. Fever intensifies the antiviral, what are called interferons, and increases productions of transferons, which we talked about in a previous segment. More transferons means more iron being taken up in the bloodstream, which means less iron available for bacteria. The increased temperature will speed up body reactions, leads to faster tissue repair, just from the fact that molecules and atoms are moving around more quickly, more rapidly, and so this is going to lead to faster tissue repair. And in some cases, and this doesn't happen in everybody, but tachycardia speeds up circulation of white blood cells. So having an increased heart rate can also be of benefit to us as well, leading to the increase of not just white blood cells, but also repair proteins and immune system proteins that are doing their job, trying to get rid of the bacteria, the viruses, and eliminate the infection from us. So don't treat a fever right away. You can let it go, as a very popular song states. Just let it go. To a certain point, of course. I mean, you don't want to let your temperature go to the point where it's going to become life threatening or where you can no longer function without being completely miserable and in pain. But if you can tolerate it, let the fever go. Let it do its work so that you can then uh, benefit from all of these processes that are going on that are trying to remove the body of the infection. And again, like I said, up to a certain point. At a certain point, it's time to get medication, or if it's bad enough, to seek medical assistance. But there are definite benefits for a fever, so let's not give fever a bad rap. Fever is good, and fever is something that is within us, and it's there for a benefit. The complement system. So the complement system, look at the word itself, complement, and it's not like compliment, like you look beautiful today, and it's so nice to see you, and my goodness, I love your outfit. No, this is complement. It's complementing something. In other words, it's helping it. It's joining in, and it's assisting. And so that's what this system is. It's a group of about 30 proteins produced in the liver, and they circulate throughout the body. And these proteins are working together to destroy microbes by cytolysis, so make them go boom, inflammation, and phagocytosis. And so again, as I mentioned, many of these proteins and the mechanisms of the immune system are all based on previous signals. It's a cascading effect. If one thing happens, that leads to the next thing happens, which leads to the next thing to happen. It's just like the clotting mechanism. The clotting mechanism is an orchestration of many biochemical reactions that have to take place in order for blood clots to form and to remain in place and to stop the flow of blood where it should not be flowing. The complement system works similarly. One event happens, that domino falls, and then the next event happens. And so the complement system is backing up, it's complementing the main actors of the immune system. Um, They also prevent excessive damage to tissues as well, which can happen in some cases where the endotoxins get released in large quantities. And then that can lead to severe damage to tissues just because of our own bodily processes trying to fight the infection. Complement system will step in and prevent excessive damage to tissues that take place during infections. So this is just one little snapshot of the complement system. So don't see this, don't look at this picture and think, well, this is the whole thing and that's all that happens. No, this is just a little segment. Remember, there are over about 30 proteins that operate together in the complement system, and we're just looking at a small snippet here, just a small handful of proteins that are involved. So C3, C standing for complement, it splits into C3A and C3B. And so there had to be a signal before that to even initiate the splitting of C3, which does happen, and I'm not going to talk about that because we're only looking at this particular part here, and this is a good starting point. What happens here? So C3b and C3a both have their own unique jobs. So we'll look at C3b there, and you can see in the picture, C3b heads off to the left, and what does it do? It enhances phagocytosis via opsonization. Opsonization is what that is called. And it also causes C5 to split into C5a and C5b. Okay, what's opsonization? So it's described here as being an enhancement of phagocytosis. So you look at that picture and you have the bacterial cells there. That's what those rod-shaped things are with the red dots on them. The red dots are C3b. So under normal circumstances, the phagocyte is going to consume these bacterial cells. But you add C3b to the bacterial cell membranes, and all of a sudden now, I don't know how else to phrase it, it just tastes better to the phagocytes. It creates a greater affinity for this process of phagocytosis. It increases the rate of it. It increases the ability of the bacteria to adhere to the phagocyte, and leads to a greater amount of phagocytosis. Remember, macrophages, that's their job. They just eat and eat, and macro means big, so they're massive cells, and compared to a bacterial cell, they're huge. So they can take in many cells and phagocytize them. What happens then in the next step, C3A and C5A, they stimulate mast cells to release histamine. And then you can see those two joining together there, where C5 is split, the yellow guy there, and C into C5B and C5A. Well, C3A and C5A join forces together, and the two of them will be attached to a mast cell, which will then release the protein histamine. And histamine leads to permeability, so that leads to the ability of neutrophils to leave the circulation and come to the area of infection, which causes a whole inflammatory response. And so we have chemotactic attraction of phagocytes. In other words, it's kind of like sending out a signal, hey guys, there is some work to be done over here. Come to this site of the infection, clean things up, get rid of these bacteria, and let's get back to business. And so that's how those two are working there. And so they're stimulating the release of histamine so that we have a greater inflammatory response. C5b now, so we took care of C5a. Let's look at what's C5b doing. Well, it binds to C6, which causes C7, C8, and C9 to join in on the fun. And so you have then these four working together, 6, 7, 8, and 9, and including C5b, so that's what, 5, sorry. The five of them working together they join together and they form this, what's called a membrane attack complex, which leads to the cytolysis of the microbe. So what is this membrane attack complex? So it's a group of these proteins that join together and then can penetrate through the microbial plasma membrane. And so as a result, a hole basically gets punctured into it, and then that leads to the bursting of the cell. Now in the picture it shows just one event happening here of the cytolytic event there. But imagine this is going to be happening at a number of places on the bacterial cell, and so it's going to just lead to the cytolysis, the explosion of the cell, so to speak. So we have here a picture that shows before cytolysis, happy bacteria doing their thing, rod-shaped bacterium, happy. And then after cytolysis, they're not looking so good, and you can see how the cell has exploded and basically broken apart due to the membrane attack complex that we just discussed. This just shows up a little close-up of what's going on here, where C3A and C5A will bond to the histamine releasing mast cell. So once those two bond together, it then sends a signal to the nucleus, which then sends a signal for histamine production to increase and then also then be released through the process of exocytosis. C5A attracts phagocytes to the site of infection. So C5A is like a signal, hey boys, come over here, we have an infection, and along come the phagocytes to do their job of consuming the threat, the bacteria. So that's in a very small nutshell, that's the complement system. So can they evade complement? Yes, just like bacteria can evade phagocytosis in a number of very crafty ways. Bacteria can also evade complement. They have adapted and evolved a number of processes in order to get around our system of trying to eliminate them and kill them. So what have they formed? They form capsules. These capsules prevent complement activation. They discourage opsonization and MAC formation. Okay, what do I mean by that? Discourage. So they're going to prevent the complement proteins from, okay, so they're gonna form their MAC, their membrane attack complex, but with a capsule, the membrane is not available for them to attack, and so therefore that can't form. They'll discourage opsonization through the inability of the complement proteins to actually adhere to the cells, the cell walls of the bacteria, and so therefore the macrophages don't recognize it as readily. Some of their surface molecules prevent formation of complement proteins that would normally kill them, and so their molecules, for example, will prevent the membrane attack complex from actually bonding together and being able to penetrate and puncture their cell membranes. And some produce enzymes that break down C5A. And again, just in this particular specific aspect of the complement system we're looking at. They produce other enzymes as well that are discouraging or hindering the complement process. But in this particular instance, this enzyme breaks down C5A, which attracts phagocytes. And so the phagocytes don't receive the signal, hey boys, there's something to eat over here. And if they don't receive that signal that there is something to eat, they're not going to come and consume. And so that signal then is lost. And then we don't have enhanced and increased phagocytosis. The last thing we'll look at are what are called interferons. Interferons are antiviral proteins produced by cells, mainly fibroblasts, which are connective tissue producing cells, lymphocytes, and leukocytes as well after viral stimulation. Now, we're going to look at just a few of them, alpha and beta. And what do? They cause cells to produce antiviral proteins that are going to inhibit viral replication so that the viruses cannot replicate themselves within the cells, get to immense numbers, and then lead to an apoptotic event, apoptosis of the cell, which then releases these baby viruses to then go out and infect other cells. So these two are working to prevent and inhibit viral replication. Gamma interferon, that causes neutrophils and macrophages to phagocytize bacteria. So here's another one like C5A, calling these phagocytic cells to sites of infection where bacteria are located. Gamma interferon works in a similar fashion. So they're typically involved, that is interferons, in acute short-term infections such as colds and influenza. So these ones that are that come on suddenly, don't hang around for a very long time, that's typically when we see the production of interferons. like colds and influenza. So how does this work? So this is showing basically a step-by-step. Viral RNA from an infecting virus enters a cell. So here's the point of attachment, penetration, and then the DNA gets inserted into the cell. The infecting virus replicates into new viruses as a result of taking over the cell's machinery and doing its the virus is doing their parasitic thing. The infecting virus also induces the host cell to produce interferon on RNA, interferon messenger RNA, which is translated into alpha and beta interferons. So this induction of these interferons are brought about by the presence of the viruses within the cell. So here's the beginning of this the beneficial effects of these interferons being produced. They're released by virus-infected host cells, the interferons, and they bind to plasma membranes or nuclear membrane receptors on uninfected neighboring host cells, inducing them to synthesize what are called antiviral proteins, even before those cells have been infected. So it's kind of like for the cell that is infected, it's like its swan song. Here we are, this is its last hurrah. So before it's overrun and overtaken by the viruses that are busily replicating inside of them, it sends out a signal to the neighboring cells. Hey neighbors, I'm under attack here, and before you also are under attack here, I'm going to send a signal to you which will induce you to make these antiviral proteins, again, before they become infected. So this is all preemptive. And notice in the picture, we're looking at just two cells. Of course, it's not that simplistic. It's sending out interferons to numerous cells that are surrounding that particular cell that is infected. The new viruses released by the virus-infected host cell infect the neighboring host cells. But little do these viruses know that the new cell, the neighboring host cell here in this particular graphic, it has already received the signal and is prepared to be under attack by the viruses because it's made these antiviral proteins. As a result, then, the AVPs, the antiviral proteins, degrade viral messenger RNA and inhibit protein synthesis and thus interfere with viral replication. And so because they have these preemptive chemicals, these AVPs, these proteins, the viruses then cannot carry out their process of replication. And then as a result of that, the cell is not infected. And so it doesn't fill up with new viruses. Viruses can't replicate, and therefore that cell then no longer becomes a safe house for these viruses to reproduce and then lead to cytolysis of the cell, and then they get released and go and infect other cells. So this is a very helpful system that our cells utilize to combat viruses, the interferon system. So that's the end of the chapter, the end of chapter 16. And that is non-specific immunity, that's non-specific defenses. I will continue making these videos like I said at the beginning, specifically for my college students, but of course these videos are available to anyone who can use them and get benefit from them. So anyway, I'll be moving on next to microbial mechanisms of pathogenicity. That will be my next topic to cover. So before I leave you, I just had some requests for you. Be sure to smash that like button, leave a comment, subscribe for more, and share this video. Thank you.